Let's now look at the properties of the hydrocarbon family called alkanes. Alkanes are composed of nonpolar bonds. So, because of this feature, alkanes of one to any type of carbon are going to be considered nonpolar molecules. Since they don't share the polarity of water, all alkanes are insoluble in water. The number of carbons in an alkane, when it's increased, the melting point and boiling points increase because the London dispersion forces are additive. Since we know that all alkanes are insoluble in water, we actually call these molecules hydrophobic because that means that they are going to be able to repel water. When it comes to alkanes and we compare it to other organic compounds, they're going to have lower melting points and boiling points. Even though they may have comparable molecular weights, but the main reason why this observation is true is because alkanes are going to exert only very weak attractions. Remember that we mostly see in these nonpolar molecules London dispersion forces. Now we're going to proceed to look at the classification and naming of alkanes. Whenever we're naming organic molecules, the International Union for Pure and Applied Chemistry, known as IUPAC, is the agency that has designed the system of how we are going to name organic molecules. And when it comes to this, and when we're naming alkanes, understand that a prefix has been designated for the number of carbons present in an alkane molecule. So if we look at table 8.4, we can see that an alkane of one carbon is called methane. An alkane of two carbons is called ethane. An alkane of three carbons is called propane. An alkane of four carbons in a row is called butane. And as long as we have five carbons or more and they are in a straight chain, we can see that now the prefix for the number of carbons is the Greek prefixes that we learned before: pent, hex, hept, oct, non, and dec. And because we're naming alkanes, every single one of those names are going to end in ane. So that's why we have pentane, hexane, heptane, octane, nonane, and decane. We can see the structures of these straight chain alkanes in the last column of table 8.4. The reality is that because organic chemistry have a little bit of a more complex structure, what we just learned in the previous slide actually is the designation of the root based on the longest continuous chain of carbon atoms. And to remind you of those prefixes, we can see them all summarized in the table that we have to the right of the slide. And we observe that they all ended in ane because the suffix that is attached to the root is going to designate specifically the functional group of that compound. But understand that at times we are going to be incorporating prefixes into the root and ending for the name of an organic compound. Those prefixes are going to be a little bit different from what we are used to from the previous chapters. Prefixes in organic chemistry are going to identify, it's going to, identify and number the branches that are extending from that longest continuous chain of carbon atoms. If we go back to the example that we did previously, when we were looking at structures, so the example that I'm referring to is specifically slide 6. We already seen some of this work. If we go back to this slide, we can see that my longest continuous chain is 5 carbons. And I see that outside of that, I have a branch. So technically, when we are naming something, and I'm just going to write the name of this compound, 2-methyl pentane. If I relate it to prefix, root, and ending, the 2-methyl will be part of the prefix, pent is part of the root, and then ane is the ending. So I'm going to take this and copy it. Let me do it with the molecule. So you can relate it to a specific example that we did before. Let me just paste it here. This is the prefix. The root. And the ending. Let's now observe other types of prefix that can be incorporated. Because remember that the prefixes are going to be the attached group that are going to extend from that longest continuous chain of carbon atoms. There are some of these outside groups, which the actual word that we use in order to talk about them is substituent. So every time I refer to a substituent, it's going to be those groups that are part specifically of the branches that are extending from the main chain of carbons, meaning the longest continuous chain of carbon atoms. We just observed that a CH3, and I'm going to zoom in table 8.5, that a CH3 is called a methyl group. If the branch, meaning the group that is extending outside that parent chain or longest continuous chain of carbon atoms, is a CH3CH2, that's called an ethyl group. If it has 3 carbons, that's called a propyl group. But if those 3 carbons, the attachment is through the middle of those 3 carbons, that's called isopropyl. 4 carbons in a row, that substituent is called a butyl group. If we're attaching through the second carbon in 4 carbon system, that's called sec butyl. If we are attaching it via a CH2 and that CH2 is connected to a CH and 2CH3, that's called isobutyl. And if we have a carbon atom connected to three CH3s, and that is a branch, that is called the tert-butyl group. All of these branches or alkyl groups, basically, these are going to be known as substituents. These are going to extend outside, still connected, but they're going to be outside the longest continuous chain of carbon atoms. In a moment, when we look at structures and we start learning how to name them, we're going to put all of this in practice. Other groups that can be found outside of that longest continuous chain of carbon atoms include halogens like fluorine, chlorine, bromine, and iodine. And you can see that in table 8.6, we have the common names for those non-alkyl groups. So fluorine is known as a fluoro group. Chlorine is known as a chloro group. Bromine is known as a bromo group, and iodine is known as an iodo group. Additionally, we can have an NO2 group, which is known as a nitro group, and we can have an NH2 group, which is known as an amino group. We are now going to put in practice how to go from a structure to putting together the word that names the following structure. So at first, we're going to learn how to name alkanes with one substituent. The steps to name an alkane with one substituent are the following. First, you're going to write the alkane name of the longest chain of carbon atoms. And remember that when you do that, essentially what you're putting together is the root of the name plus the ending. And essentially, since we're naming alkanes, that ending is going to be ANE. Next, you're going to number the carbon atoms in that longest continuous chain of carbon atoms, starting at the end that is nearest the substituent, meaning the group that is extending from the main chain. Next, we're going to write location and name of the substituent as a prefix to the name of the main chain. Remember that location and the name of the substituent are separated by a hyphen. So let's look at the examples that we have on the right. Here I have a condensed structure. First, I'm going to find the longest continuous chain of carbon atoms present. I'm going to start mapping out how many carbons I have in a row. 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5, 6, 7, 8. But there's another route that I can take in this molecule. 1, 2, 3, 4, 5, 6, 7, 8. Since those are the two routes that I have from end to end in this molecule, it doesn't matter which one I select. Both of them are going to result in the same name. So I'm going to highlight the parent chain. And remember that you could have chose the one that I selected previously. It will result in the same name. Now I'm going to number this chain, starting from the end that is nearest the group that is outside of that main branch, that we can see that CH2CH3 is closer towards the right of the molecule. So we're going to number this as 1, 2, 3, 4, 5, 6, 7, and 8. I can observe that in order for me to name that main chain, since I have 8 carbons, I'm going to put the root oct. Since this is an alkane, it's going to end in ane. So that longest continuous chain is known as an octane. Now I'm going to proceed to put the prefix. In the prefix, I can see that at position 3, I have the substituent. And that substituent is specifically a CH2 followed by a CH3. If you go back into the slides explaining alkyl substituents, that group is called an ethyl group. Let me highlight it. So the name of this molecule is 3-ethyl octane. Let's look at the next example. In this skeletal structure, my longest continuous chain of carbon atoms is 1, 2, 3, 4, 5, 6 carbons. I'm going to number it. 1, 1, 2, 3, 4, 5, 6 carbon atoms. So, taking that into consideration, I'm going to write now the alkane of that longest continuous chain, the alkane name. Since I have 6 carbons, the root is hex. Since I have an alkane, this is hexane. Next, at carbon 2, I have a prefix that it's going to symbolize that I have the following substituent, which is a chlorine. So this is 2-chlorohexane. And let me just finish highlighting the 2 comes from the location of the chloro group in the hexane chain. And that's how you name alkanes with 1 substituent. Now let's learn how to name alkanes with 2 or more of the same substituent. Step 1, we're going to find the longest chain of carbon atoms and write the alkane name. Next, we're going to number the carbon atoms starting from the end that is nearest to the first substituent. Next, when we have 2 or more of the same substituent, we're going to additionally add to the prefix di, tri, or tetra, or so on, penta, hexa, hepta, if you have to represent, I should say, the number of the same substituents that you have. Then the number for the locations of these substituents are separated by a comma. And every time we have numbers and words, we are going to use a hyphen to separate them. Let's look at the examples that we have on the right side of the slide. Let's look at this molecule. When it comes to this molecule, and I'm trying to investigate what is the longest continuous chain of carbon atoms, understand that I can select 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. Any of them will give me the same name. In this case, I'm going to select this one. to get you guys to start thinking that the longest continuous chain not necessarily is going to be the one from left to right. It's going to be in any direction possible. So, taking that into consideration, the alkane name for the longest continuous chain of carbon atoms is going to be pent, because I have 5 carbons, and since I have an alkane, it's going to be pentane. When I number this, I have to start from the end that is nearest the substituents, and that is going to be the left side of the molecule. So I'm going to number this as 1, 2, 3, 4, 5. Those substituents are located on carbon 2, both of them. So that means that I'm going to say 2, 2, because both of them are on carbon 2. Di, because I have 2 of the same substituent. And that type of substituent, since it's a CH3, is called a methyl group. So this is 2, 2, dimethyl pentane. Let's look at the next example. Here we have a skeletal formula. The longest continuous chain of carbon atom. If we go from this end, we say 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Oh, 7 is longer. Let's just try one more route. 1, 2, 3, 4, 5, 6, 7, 8. So the last one that I highlighted is the longest carbon chain. Other possible ones would be 1, 2, 3, 4, 5, 6, 7. That's not as long as 8. Or 1, 2, 3, 4, 5, 6. That's not as long as 8. So that means that this stands as my longest continuous chain of carbon atoms. So since there's 8 carbons, let me number them. 1, 2, 3, 4, 5, 6, 7, 8. That means that the long chain, its name, its alkane name is going to be oct for the 8 carbons, ane because this is an alkane. Okay. This molecule will result in the numbering 4 and 5, even if I do right to left or left to right. So I'm just going to do left to right to simplify it. But please make sure that you number it from right to left so you can see that the 2 branches that are extending from the octane are actually in position 4 and 5. If you number it starting from this end and moving towards the left of the molecule. So those 2 groups that are extending at positions 4 and 5, because technically there are 2 carbons there, because there's a carbon right here and a carbon right here, then that means that those are ethyl groups. So how I write that is that I'm going to say on carbon 4 and on carbon 5, I have 2, meaning di ethyl. And those 2 groups are extending from the octane, which is the longest carbon chain. Let's now look at how do we name alkanes with different substituents. We can observe that regardless if you have one substituent, multiple of the same, or different substituents, the first rule is always the same. Find the longest chain of carbon atoms and write the alkane name. Similar to what we observed before, we're going to number the carbon atoms starting from the end that is nearest a substituent. And lastly, because we're going to have multiple substituents, let's understand that this is going to give us the idea that when we have to write the location and the name of the substituent, since we have multiple, And they're going to be different at times when we write them as a prefix of the root and ending. We have to write them in alphabetical order. Always remember that numbers and words are separated using a hyphen. Let's do the examples that we have on the right side of the slide. In the first molecule we can select the longest carbon chain as carbon 1, 2, 3, 4, 5, and 6, or carbon 1, 2, 3, 4, 5, and 6. Both will give you the same answer. So I'm going to select specifically this. And now, when I number my substituents, if I start from left to right, this is carbon 1, this is carbon 2, 3, 4, 5, 6. That means that my first substituent is on carbon 2. But if I number the molecule from right to left, meaning this is 1, 2, 3, 4, 5, 6, my first substituent is also on carbon 2. So which direction should I number? Well, understand that it will depend on what is the overall lowest number that you can give those substituents. So let me actually write the numbering in both directions so you see what I mean. So in the direction going from left to right, I will say carbon 1, carbon 2, carbon 3, 4, 5, and 6. And then in the direction that goes from right to left, this will be 1, 2, 3, 4, 5, and 6. So I'm going to write what would be the numbering and name for the substituents in this molecule. Regardless, the parent chain of this molecule is going to be called a hexane. So in the numbering that I did in red, that means that on carbon 2, I have a fluoro group. On carbon 3, I have an ethyl group. And then on carbon 5, I have a methyl group. If I do the blue numbering, which is the one that is going from right to left, then on number 2, I have a methyl group. On number 4, I have an ethyl group. And then on number 5, it's going to be a fluoro group. Okay? So when I investigate the numbering, I can see that I can give a 2, 4, 5 versus a 2, 3, 5. The smallest overall numbering that I can give to this molecule, it will be the 2, 3, 5. Because you can see that then I'm grouping those substituents to the lowest number possible that I can give them. Because in essence, when you look at the numbering, the fluoro and the methyl could either take positions 2 or 5, but since I can give in this numbering an ethyl position 3, then that's why the red numbering is the correct one. So let me just erase the blue numbering. I know that my longest carbon chain is going to be a hexane. Now I will proceed to put those substituents in alphabetical order. So the way that I write the name is going to be at first 3-ethyl, 2-fluoro, and then 5-methyl. And those are the three substituents that are extending from the hexane chain. Let's look at the next example. Here we have a skeletal formula. In this skeletal formula, we can see that our longest continuous chain of carbon atoms has 1, 2, 3, 4, 5, 6 carbons. So that means that that chain is called hexane. Then, when it comes to numbering, if we do left to right, fluorine is on number 2. But if we do right to left, fluorine is also a number 2. So that means that we have to investigate what is the lowest possible number that we can give that bromine, depending on where we start. Because in either direction, the fluorines are getting a position 2. So because of that, we need to investigate what happens to the bromine group. And from practice, you can imagine that doing numbering 1, 2, 3, 4, 5, 6 is going to be basically determining that we can actually give bromine a number 3, because in the other direction, meaning going from left to right, then bromine will get a 4. Okay. Now, when we proceed to write the substituents as a prefix of our parent chain, that is a hexane, then we have to keep in mind that our substituents are on position 3, we have a bromo group. In positions 2 and 5, we have 2, that's why di. And then fluorines is called fluoro groups. Okay. Now, these two different names for the 3 substituents that we have in this molecule, we have to put them in alphabetical order. I want to bring to your attention that if you have substituents in which you have a group of 1 that is multiple versus a single one, the prefix di, tri, or tetra is never alphabetized. In order to alphabetize these substituents, you're comparing the F in fluoro to the B in bromo. You're not comparing the di to bromo, okay? So from there, to actually put the positioning and the name of the substituents in alphabetical order, I'm going to write 3 bromo, 2,5 difluoro, hexane, and that will be the name of this compound.